Honors Algebra 2, Chapter 7, Section 4. So we're going to look at logarithmic functions. And so let's first begin with solving these equations and what we would do to both sides. For this one, we would divide both sides by 2. And why do we divide both sides by 2 is because we're multiplying here. Here we're dividing by 3, so we want to multiply both sides by 3. Here we're adding 2, so we're going to subtract by 2. So it's doing the opposite operations. Here it's x squared. The opposite there is going to be square rooting. And from last try, we should know that that x value is going to equal plus or minus 4. Don't forget plus or minus. Here we're doing the cube root, so the inverse of that is doing the cube power. Now what is the inverse of this? We have 3 to the x power. So this is your exponential functions. And so that's what we're going to look at today, is what is the inverse of an exponential function. And that's going to be called the logarithmic function. So logarithmic functions are inverses of exponential functions. So how do you find the inverse of y equals 6 to the x power? Well, if you think about last try, how do we find inverses? You should recall that you switch the x and y. So you have x equals 6 to the y power. And then you try to isolate y. We're back in the same situation. We have the variable we're trying to solve for, or evaluate in the x part, so that's the issue. And so we have this notation, is that this is going to be equivalent to me putting it in log form, which is going to be log, whatever my base is, base 6, so our base here is base 6, so log base 6 of x is going to equal y. And basically what you do is you switch the x and y to put it in this form, to go from exponential to log form. So these right here are the same thing. One is just written in exponential form, one is written in log form. So this would be the inverse of the original equation. So by definition, the logarithm of y with base b, log base b of y equals x, if and only if b to the x power equals y. So you notice how the x and y's are switching spots. So let's put these in the different forms. So this is exponential form. So in exponential form, you do not have the word log. It's an exponential form. So 3 to the x power equals 9. To put that in log form, you write the word log before it. Now our base 3 stays the same. So log base 3, it's actually a little 3 below the log. Then the exponent and the result switch spots. So log base 3 of 9 equals x. So this will be log 4. The next one, log our base, which is 5, and then whatever it equals, which is not stated. So sometimes I just make it a variable. So log base 5 of m equals 0. So this last one here, log base 6, and we just switch the 1 and the 6. So log base 6 of 6 is 1. So those are going from exponential to log. Let's go the other way, going from log back to exponential. To do that, whatever our base is, the little numbers are base. So 2 to the power of, now these two switch spots. 2 to the power of 4 equals 16. So most people prefer the exponential form, but we gotta come to this log form. We're going to see it a lot. Next one would be 3 to the third power, which is 27. The third one, our base is 4. And then the 2 and the 16 switch. So 4 squared is 16. Next one, 3 to the x power is 9. So this one's a good example where in log form you may have a hard time seeing what the answer is, but writing in exponential form is pretty easy to see. It's going to be 3 squared is 9. The last one does not equal anything, so we can make it like equal n. And then we could write it like 3 to the nth equals 81, which helps me see that the n here is actually 4. So some special cases. Logarithms of 1. Log base b of 1 has to equal 0. And that's because it comes from this exponential property. B to the 0 power is 1. Anything to 0 power is going to be 1. And so you put that into log form, you get another property just in log form. So log base 14 of 1 is just 0. Anything log base anything of 1 is 0. Logarithm of b with base b. So we have log base b of b has to be 1. Again, you put that in exponential form, you should see b to the first is b, how that makes sense. Put that in log form, it's still true. So log base 7 of 7 is 1. Okay, inverse properties. Log base b of b to the x is x. If I put this in exponential form, it may help you realize how this is true. Our base is base b, so b, and then b to the x power has to equal b to the x. So that is true. That is equivalent. So this is got to be a true statement. Log base b of b to the x is x. So for this example, we have log base 5 of 25 to the x. This 25 isn't the same as 5, so we don't have that b and b. So the answer is not x. We have to manipulate this to make 25 be a base of 5. So I can write that as log base 5 of 5 squared to the x power, and then squared to the x power is just 2 times x, so 2x. Now I can see that this is going to be 2x. Log base 5 of 5 to the 2x. You can think about it as log, we have a log, and then we have an exponent, so we're doing inverses, so we're undoing what's occurring in the problem. It's like multiplying, then dividing. For this one, we have the exponent first, so b to the power of log base b of x. So we're doing a power to a log, so those are inverses, and we just get x. So 10 to the power of log 4 is going to be 4. Now for this one, we've not seen yet today. If this is log 4, it doesn't show our base. When it doesn't show our base, it is base 10. So now you can see it's 10 to the log base 10. Those are the same bases. So we can manipulate these same way to evaluate the problems. We can change them to exponent form, but I'm hoping we can put these in, manipulate them so we have that log base 4 of 4 to some power. And so I'm trying to rewrite this log base 4 of 4 to what power? Well, 64 is 4 cubed. So once I see that, then I know that this has to be 3. Log base 9 of 3 is equal to log base 9 of 9 to what power? So 9 to some power has to be 3. We should see that this value here, we got to do like square root of 9 is 3. So that's 9 to the 1/2 power. So that's going to be 1/2. So we're using a lot of our number sets. All of our exponent rules, log base b of 1, log base b of 1, this one log base 5 of 0.04. To help me out, I'll put that into fraction form. Log base 5 of 4/100ths, which is 2/50ths. Now I want to have it the same base. This is log base 5 of 5 to what power? So we'll move 25 to the numerator, so it makes a negative exponent. And then 5 squared makes that equal to 25. And so I can see that's just going to be -2. For this one, we'll have this be your video problem. I'll have you try this one. This is a little more difficult. You have to write 8 using a base of 1/2. And then for this is a rule we should know. Log base b of b is 1. So common log, we talked about that already. Log, when you don't see our base, it is base 10. So log base 10 of x. So we can write this as log base 10 of x is the same thing. The natural log, ln is the natural log, and that's log base e of x, which we've seen from previous day, our e value. So log base 1000, or log 1000, it means log base 10 of 1000. So to evaluate that, I write that log base 10 of 10 to the 3rd power, find out that value is 3. So you should be at the point where you should be able to evaluate that quickly without having to manipulate too much. For this one, I can write this as e to the power of ln, again, is log base e of 9. Well, now I have those are inverses, e to log base e, so it's just 9. So down here we can use our calculators. The log key and the natural log are on your calculator. These down here, you can just plug and chug and say log 14, evaluate, you can find the value. So the calculator will help us find log base 10s and log base e. It'll find those two quickly. Inverses. Review from previous try. To find inverse, we switch our x and y. So x equals 3y minus 2, and then we solve for y. So x plus 2 equals 3y. We multiply 1/3, so 1/3 x plus 2 thirds equals y. And that'd be our inverse function. We can do the same thing with exponents for here. We can switch our x and y. So x equals 8y, and then put in the log form. So log base 8 of x equals y. This is the natural log, so this is y equals log base e of x minus 4. So I can still switch my x and y, put it into exponent form. So this is going to be e to the x power equals y minus 4, and then add the 4. This will be the inverse function. This will be your other video problem, 2 video problems. Go through the same steps we just did with this problem, which is the common log base 10. Graphing. If we graph this exponential function, we have a horizontal asymptote here, and we have points. 1 is our awesome a value, so 0, 1. Every time I go to the right one, I'm going to multiply by 3. And if I go to the left, I'm going to be dividing by 3 and multiplying by a third. So then we have this shape. So if I want to graph the inverse, this point 0, 1 becomes 1, 0. This point here, 1, 3 becomes 3, 1. Our horizontal asymptote, remember from last try, our inverse functions are reflected over the y equals x line. So if I flip a horizontal line, reflect it over that, we get a vertical line. So our asymptote becomes a vertical line. So then we have our graph is going to be approaching that asymptote and then going through these 2 points. So this is the graph of the inverse function, which if we put it in the log form, that is the inverse. So it's going to be log, same base, and then log base 3 of y equals x. And then we should switch our x and y to actually write the inverse. And this is the inverse function. And so the red graph here is an inverse of the black graph, which you can also see is true for the equations as well. And so to help us graph, from graphing this function to begin with, I typically use the log base 3 of 3 is 1, and I use log base 3 of 1 is 0. Just the properties that 3 to the first power, or 3 to the first power is 3, and 3 to the 0 power is 1. I use those 2 rules in log form along with my vertical asymptote to graph it. And that's really what I do to graph logs. You could put this back into exponential form and then graph that as well if you really need to. So example here for this one, a few ways to graph it. Option A is to actually find some points. So let's do it that way. That's the way I try to do it. And I like it doing this way because it makes me more familiar with the log form. But if you notice, we don't have a single value here. We have a shifting. So this is really like log base 4 of some parenthesis equals 1. So now this parenthesis has the plus 2 in it. So what can our x value be? It has to equal 4. So it's got to be a 2 value. So now I have my point x comma y 2, 1. So this is log base 4 of our parenthesis, we have the plus 2 in it, equals 0. And we need this parenthesis here to equal 1, so this has got to be negative 1. So our point is negative 1, 0. Now our asymptote for the parent function is our y-axis, or x equals 0. But what does this plus 2 do the graph? It shifts it left 2. So our vertical asymptote becomes this line, x equals negative 2. So here would be the shape of the graph. All of our log graphs have that shape, unless we've been reflected or shifted or stretched. But this would be the typical shape of the parent function. And that's it for the video. You can enjoy the nice background here, which is a shape that uses logarithmic functions that's developed from nature. So have a good night.